Hi folks, in this video we're going to be talking about how you can build an equation based on the relationships that we figured out earlier, and we're also going to learn some mathematical operators, which are symbols that we tack onto our variables to help us be a little bit more specific or do something interesting with them. I think one of the common misconceptions about physics is that we'll be using a ton of these equations that some genius physicist came up with, and we don't really understand how they work, but we stuff numbers in one side and other numbers come out the other side. Equations are actually an incredibly beautiful and elegant way to explain the way the world works. They allow you to predict the future and explain the past, and I think that you miss out on a lot if you just trust other people's equations. So throughout this class, we're never going to tell you an equation. Instead, you're going to be building your own equations. You're going to be creating them, and when you create them, then you own them. Of course, you haven't had this skill before. You don't know how to make an equation. And we want to make all these equations that explain things that we're interested in, an equation that acts like a pendulum or a spring or a car or a planet. But the good news is that the building blocks of making equations are these relationships. So we can run experiments, we can use our own intuition. We need to figure out what variables control the behavior of the object we're interested in and what kind of relationship it has. Then you just have to combine those relationships into making an equation, which is an incredibly powerful tool that we'll be using throughout this class. So let's say it's the first week of school and you want to make an equation to figure out how nice your teachers are. And you and your friends decide that teacher niceness, or N, is related somehow to the amount of candy given out by that teacher, which is a variable C. So you make a graph of teacher niceness versus candy, and you notice a couple things in this graph. The first is that N is the dependent variable, right? That's the variable that is determined by how much candy. The niceness depends on how much candy they give. So it's on the y-axis, and it's my dependent variable. C, the candy, is the independent variable. And when you look at the graph, you put your nice best fit line in there. That's some good looking data. But you see that there's a linear relationship between niceness N and candy C. So how do you start to build this equation that reflects this linear relationship between niceness and candy? Well, the dependent variable goes on one side of the equal sign. And then any independent variables that you found that have a linear relationship, like the candy, are going to go on the top of the other side of the equation. We don't have a denominator right now, but that means that your equation right now with that single relationship looks like this: N on the left and a C on the right. There's a little asterisk there because we may be adding some more things on the right side of the equation. If we figure out there's other variables that are going to impact teacher niceness, we got to add them to that right side of the equation until the equation's complete. So why does this work? Why does it work to have one variable on the other one side and the other variable on the other when we have our linear relationship? Well, that equal sign means the two sides have to be equal. If I double one side of that equation, the other side of the equation, to keep up with it, is going to have to double. And that's the way linear relationships work. If we double the amount of candy, the niceness has to double to keep this math expression balanced. If I make one side smaller, if I decrease the amount of candy, well, the niceness is going to have to decrease as well in order to keep that equal sign balanced. So that's why when we have a linear relationship, we put one of the variables on each side of the equation. Now let's say that your friends have decided that teacher niceness also depends on a different variable, which is homework they assign, or H. And the more homework that teacher assigns, of course, the less nice they are. So when you make a graph of the amount of homework assigned versus the teacher niceness, you see not that nice linear graph, you see that inverse graph that shows that when one variable gets big, the other variable actually gets smaller. In this graph, N is still the dependent variable. Okay, the niceness depends on the homework, and so it's the niceness is on the y-axis and the homework is going to be on the x-axis. This graph, as I mentioned before, shows an inverse relationship where one variable increasing causes the other variable to decrease. So how do you build this equation using that inverse relationship that we just figured out? Well, just like we did before, we're going to leave our dependent variable on one side of the equal sign, but this time on the other side of the equal sign, we're going to put our independent variables on the bottom, on the denominator of the other side of the equation. So it's going to look something like this. Niceness on one side. On the other side, we have a 1 over h. Okay, we have an h on the bottom. And we have an asterisk again because there might be other stuff that affects niceness, but we know that one thing that's in there is the homework, and it is an inverse relationship, so it's going to be on the denominator. Why does it work to have niceness on the denominator on the other side of the equation? Well, if you remember how fractions work, if homework gets to be really, really big, if I double or triple or quadruple homework, right, the fraction that represents homework, the 1 over h, is actually getting really, really small. So by doubling homework, I'm making the right side of the equation 1 over 2, or 1/2 as big as it was before. So to keep up the niceness on the other side of the equation, you need to have a 1/2 added to the niceness. So by making homework larger, we're actually having to make niceness smaller in order to keep this equation balanced. So let's say you and your friends have decided that candy given out and homework assigned are the only two variables that impact a teacher's niceness. And you're ready to make an equation so you can predict the niceness of future teachers given that information. You need to combine those two relationships into a single equation. So the way you do it is you leave the dependent variable alone on one side of the equation, and you're just going to multiply together those independent variable expressions that you've come up with earlier on the other side of the equation. So for example, we've got this now, n on the niceness is equal to c, the candy given out, times 1 divided by the homework, right? That's the direct relationship with, or sorry, the linear relationship with c and the inverse relationship with h. If you wish, you can simplify this. Of course, c times 1 over h is the same as c over h, and that's kind of a simpler looking equation, but it does the same thing mathematically. You'll notice this equation no longer has that little asterisk next to it because you've decided you're confident that you know all the relevant relationships, which means we can now officially call this an equation. N is equal to c over h. And you built it yourself, which means you own it. You understand the way it works. You understand why the c is on the top. You understand why the h is on the bottom. And you understand how changing one of those variables will affect the niceness. If you double the candy given out, niceness is going to double. If you double the homework given out, niceness is going to halve. And you can see that right in that equation. I'm going to go through these slides pretty quickly, but anytime you make an equation, you can test your equation. It should behave predictably, and so you could make a data table that shows how changing one variable while keeping the other one constant affects the dependent variable. So for example, if you had 2 homeworks and 6 candies given out, you can calculate that's a niceness rating of 3. If I keep the homework the same and double the candy, well, we're predicting the niceness should double. If you run it through that equation, you discover that it does. If instead of doubling, we make the, hold the homework constant, but we make the candy 1/3 what it was before, so we went from 6 down to 2, then the niceness should go down by a factor of 1/3. And if you run it through that equation, you find that it does. So good news, it's working so far. You can run another test where we are going to, this time, hold the candy constant and see what happens when we change the homework. So if we have 2 candies and 6 homeworks, well, that's a niceness rating of 1/3. Now let's try it again. 2 candies still, but this time we're going to double the amount of homework. We should predict that my niceness should go down by a factor of 1/2. So if you run the math, you find that the niceness is now 1/6. So we're half as nice as we were before. This time we're going to have the same candy, but instead of doubling the homework, we will make you have 1/3 as much homework. So instead of 6 homeworks, we now have 2 homeworks. That should allow my niceness to go up this time because less homework should make me more nice. This is now a teacher of niceness rating 1. So you did it. You made an equation that captures both of the relationships here and lets you predict how nice any teacher will be if you can measure the candy and homework they give out. And it's not a black box. You understand when you plug numbers in there why the numbers that are coming out are rational, are reasonable, and why they match your predictions. So before we go on to start to make some real physics equations that describe slightly more physicsy things than teacher niceness, I need to talk here about mathematical operators, because you'll see some symbols that I'll be using throughout the rest of the class, and I want you to understand what they mean. Math operators are symbol shortcuts that tell you to do something with a number. You've seen these before, right? The plus sign tells you to add two numbers, minus sign tells you to subtract them, square root, that less than and equal to or equal to sign. You've seen those before, and you'll probably see those throughout this class. But there's some new ones as well. So one of the new things that you'll often see on a variable is a subscript. This is used to clarify or personalize a variable that might have a number of different values in a problem. So for example, we will often use these initial and final subscripts. If we're talking about a moving object, you might say it starts at 6 miles away and it ends at 4 miles away. Well, they're both distances, but if we just write d equals 6 and d equals 4, we might get confused about what those d's mean. So instead, we're going to have this little d with a little I, a subscript I, and that tells me we're talking about an initial distance, or d with a little f, and that tells me we're talking about a final distance. You often sometimes encounter subscripts when a variable is specific. So if you had a v dog, then we're obviously talking about the velocity of a dog. Or later on, you'll learn about different forces, which are F, and F gravity, of course, refers to the force of gravity. Some other new operators that you may or may not be familiar with. A delta, which is like a triangle, is otherwise known as the change in a variable's value. So if you see a delta before a variable, what I'm interested in is how much that variable is changing over time. Not the initial value, not the final value, but how much it's changed. You can always calculate the change in a value by taking the final value and subtracting the initial value. But for some people, it just makes more sense to just think it through to figure out what the change is. So for example, if the initial time is 2 minutes and then the final time of something is 9 minutes, well, the delta t, or the change in time, is 7 minutes. It's the amount of time that activity took. It started at 2 and ended at 9, so the delta t is 7 minutes. Or if an object starts with an initial distance of -40 meters and then it ends up at a final distance of -50 meters, the delta d is -10 meters. So your delta can be positive or negative. This thing changed by -10, so its delta d is -10 meters. Another operator is the average operator, which sometimes is just abbreviated AVG. So if you see a variable with a subscript AVG, I want the average value of that variable during a certain amount of time. I know you found averages in the past, but the way you do it is you just add together the values. For us, we usually just have initial and final, so it's just adding two values together and dividing by 2. But you could also just reason it out and think about what value is right in the middle of the two values you have. So if you have an object with an initial distance of -40 and a final distance of -50, the d average is -45 meters. That's its average distance. I want to point out here that we used the same two initial and final values for distance on the last slide. We were calculating delta d. Delta d's value is -10. D average is -45. D initial is -40, and D final is -50. So all of those variables have really different values, and they're not interchangeable. You can't just use any old d in an equation. You have to use the right d, or you're not going to get the right value. The next operator is known as sigma, and it kind of looks like a funky E. You may have seen that. It's a Greek letter, and it sometimes appears on frat signs or things like that you may have seen in movies or on college campuses. But in math, that sigma means the sum or the total. So if you're interested in the sigma of a value, you just have to add up all the individual values. If you have 3 friends and each of them has $10 and you have $5, you want to know how much sigma money you have. You just want to know the total money that you guys have all together. It's going to be $35. So a quick summary of this lecture. You can build an equation out of one or more relationships. Equations are not mystical black boxes. They're actually just shortcuts that let you predict the future and calculate unknown values a little bit more efficiently. Incidentally, you can reverse the process. If you have an equation that you know, you can actually use that to help tell you something about the relationships that are impacting the variables. So it's pretty interesting to go forward and backwards using equations. When you have equations or any number in your class, please pay very close attention to the math operators that you see, because they can actually totally change the meaning and the value of a variable. Thank you very much.